Dr. Saravanan, sir. Dr. Saravanan, sir.
Hi, கேக்குதா?
கேக்குது. Dr. Kalavati, ma'am, shall we start?
Yes, sir. Good morning to one and all present here. On behalf of Rajapalayam Rajus College and Department of Physics, I welcome all for the International Faculty Development Program FDP 2.0 on recent research in material physics. Today's chief guest is going to deliver his speech. I welcome Dr. Saravanan Rajendran sir. I welcome all the participants. Welcome you one and all again.
Good morning, all of you.
Rajas, I invite Rajas sir to give the introduction about the chief guest, today's chief guest.
Thank you, madam. I'm pretty happy to be here to introduce our chief guest, Dr. Saravanan Rajendran, who has done his BSc Physics at American College in the year 2012 to 2015. And after BSc Physics, he completed integrated MSc and PhD in Indian Institute of Technology, Mandi, India. Currently, he is pursuing postdoctoral fellowship in Fritz Haber Center for Molecular Dynamics, University of Jerusalem, Israel. He has published many international journals, and he was a teaching assistant in computational chemistry, theory and spectroscopy, waves and particles, computational chemistry, and kinetics and catalysis in IIT Mandi from 2017 to 2020. Then he has given many research talks in various colleges, in national and international level. Thank you so much, sir, for giving introduction about you. Thank you, sir.
Thanks, sir, for introducing. Allow me to share screen. Yes, I can see that the screen is visible, right? So, good morning, all of you. Today, I will be delivering a talk which is slightly different from the talks that you have been listening to. So, I will talk about the current trends, the new solvable models in statistical and quantum mechanics in the time domain. So, why do we need to? You are free to interrupt me if something is not clear. So why do we need to have solvable models? Because the solvable models capture the general features of general features, patterns, and macroscopic laws uh, behind molecular systems. And then by time domain, I mean that we do not solve them in the Fourier domain or in the Laplace domain. So I will start by introducing the physical background of my talk. So assume that there is a diatom like a nitrogen N2 molecule. So if they are in gaseous phase, you can think of them as a harmonic oscillator, and then they will oscillate. If they are isolated, the total energy is conserved, so the energy will not dissipate. The molecule will be vibrating forever. But assume you put the same diatom into a solvent where the solvent modes are coupled to the modes of this diatom, and then they extract energy. So in that case, you see in the right hand side, what happens is that you start with the diatomic wave packet. Slowly it loses energy and settles to the bottom of the harmonic oscillator, where the motion of this diatom ceases. So these are the two different limits of the molecular physics, where in one case you have chemical reactions that are happening in the gaseous phase, and there are chemical reactions that are happening in the condensed phase, meaning this if they are inside the solvents. So in the first case, you know that the energy is conserved, and in the second case, the energy is not a constant of motion; it is dissipative, and the time evolution is unitary, meaning the system once propagated forward can actually equally propagate backwards. But that is not true in the case that you see in the right hand side, because the system that one has lost its energy, then the process is irreversible. So for such systems where the process is irreversible, you can think of that this molecule has a Hamiltonian which is given by the system Hamiltonian Hs, and they are coupled to a thermal bath where the system's energy is coupled to the coupled to different harmonic oscillators, and then they extract the energy. So in the conservative limit, the equation that governs the motion of this wave packet is called the time dependent Schrodinger equation, and we know how to solve the Schrodinger equation. If given that if the Hamiltonian is integrable, then you know how to obtain the closed form solution. So what are you going to get by solving Schrodinger equation? You are going to get the probability distribution, which is normalized. On the other hand, if you insert your molecule in a solvent bath, then you will have random forces, and then you will have viscous forces, which extracts which actually extracts energy out of the nuclear coordinate. And then if you do a noise averaging, you will find an equation which is similar to Schrodinger equation but not exactly Schrodinger equation. Um, and then they both have a similar form, and they can be transformed by a imaginary time transformation. If I take t gives imaginary time, then I can get a Smoluchowski equation, and vice versa. So here also we are supposed to get a probability distribution, because uh, the system is not deterministic. There is a random force from the solvent, so the molecule might move in either direction, just like the Brownian motion. So you insert a pollen grain, and then they can have random forces, and then they can move either ways. And in the long time limit, it should attain what is called the Boltzmann distribution. So what are the examples? Just like I mentioned, that for the molecules that are isolated from the environment, they undergo unitary Schrodinger dynamics. For example, gas phase spectroscopy process, gas phase chemical reactions. And in the non-unitary dynamics, the molecules that are present inside solutions, for example, you will have electronic relaxation of dyes, the electron transfer process inside solvents, the Brownian motion, or even large molecular systems. Even if they are isolated, they behave non-unitary, because the system loses much of its energy to environmental degrees of freedom. So here I will show one example of how the process happens. The aim of my research was to quantify the dynamics that happens at a molecular level by solving mathematical models. So this is called an electron transfer process. You can see that there is a coordination complex in presence of water molecules, and so there are two coordination complexes. For instance, it doesn't matter which molecule it is. um, so first they solve it according to their so you can see that they relax according to the solvent environment. The water and the molecules relax, then they come close together, they diffuse together. They may diffuse in either directions, but they can encounter a particular instant is an encounter. And once they come together, and then after the activated, oh, yes, excuse me, is the screen visible now?
No, sir. No, sir. Now okay, sir.
No?
Now okay.
Okay. So once they encounter each other, they form what is called activated complex. And once they form activated complex, they are ready to form electron transfer. And then once the electron transfer has happened, again they reorganize once according to their solvents. So here you note that there is a two time where the molecule reorganizes according to the solvent. So let us see if we can capture this general feature by using our theoretical model. I will show in the future slides. So and once the electron transfer process is over, they just move apart. So now I assert that such molecular complex processes can be reduced into simple partial differential equations that you see in the screen. So the reduction is not simple. I'll show how one can reduce the molecular processes into such coupled equations, and I will explain what does these equations mean in the upcoming slide. So how one can start? One can start from writing a full Hamiltonian Schrodinger equation for all the electrons, all the nucleuses, and all the solvent coordinates, because all these atoms are governed by quantum mechanics. So this is the Hamiltonian. I have written the sum of all kinetic energy contributions, sum of from electron, from nucleus, the electron interactions, the electron nuclear interactions, the nuclear interactions, solvent interactions, solvent and chemical species interactions. So now this is in the lab fixed coordinate frame. So imagine if someone is dancing and you are seeing from some part of the stage, and if you can transform the reference frame to the person who is dancing, you can look how his hands and legs are dancing relative to his center of frame. So in order to understand that, we do the center of mass transformation to the molecules, where if you see, you will understand the dynamics into vibrational degrees of freedom, the translational row vibrational degrees of freedom, which is not facilitated in the lab fixed frame. So one can do this center of mass transformation and can reduce the total Schrodinger equation, and the total wave function can be expanded in terms of electronic wave function and nuclear and solvent wave functions. One can always do this because the completeness allows it, and then you can reduce the which gives us the equation for the to propagate the nucleus in an nth electronic index. So you can see that so if I express the total wave function in terms of electronic wave functions, you can see that the coupling can be due to electronic and can be due to nucleus. The understanding is that if there are two molecules and they can interact either through electronic overlap, the orbital can overlap, and then they can have a bonding or interaction. And this term means that the nucleus couples various different ways where the molecules can evolve. So in the choice of electronic basis, one can have an electronic one can have the K shell, Lth shell, the electronic basis of the molecules, or one can choose a basis that is very convenient to them. For example, if I choose an electronic basis, then the Hamiltonian is almost exactly diagonalized. So you can see that the molecule, if you propagate the molecule, it can evolve from an initial state to the final state, meaning the reaction can happen on a single surface. But in the diabatic coupling, this is called the diabatic representation. These are the two different representations of the same problem. So in the diabatic representation, the molecule just evolves and the reaction is mediated through electronic overlap. So these are the two different representations of molecular process. One can solve models like this and get information, or models like this. So So in context of electron transfer, you have only two states, that either the initial state where the electron has not transferred, and the final state where the electron has transferred. In the diabatic representation, as I told, that the coupling is actually, the coupling meaning is the is responsible for the population transfer from the initial state to the final state. So in the diabatic representation, the electronic overlap mediates the electron transfer. Here the H dash is a nuclear Hamiltonian. In the adiabatic representation, the nucleus mediates the initial state to final state transition, just like that I have just shown you. So in the adiabatic picture, the nuclear motion couples initial and final states. So far now we saw that the coupled equations can capture the electron transfer or any molecular process where there are multiple states available. Maybe it's an excited or ground state, or it is a reactant or product state, or it's a covalent state or ionic state. It depends on the particular molecular process that you are interested in. In the context, if the molecule is in gas phase, then you need to use coupled Schrodinger equation. And if the molecule is present in a dissipative environment, meaning a solvent environment, then you need to use coupled Smoluchowski equations. So these are the coupled Schrodinger equation, where this is the Hamiltonian of coupling which mediates the population transfer. This psi1 and psi2 are the populations, the probability amplitudes, and this is the Schrodinger equation just extended to the two-state problem. And u of I, ux can be diabatic or adiabatic potential. I have mentioned only diabatic because we will be speaking about the diabatic picture. In the statistical mechanics, one can also write a coupled Smoluchowski equation, which is responsible for the population transfer. Here you can see that you remove some population from the first state and put it in the second state, and remove some population from the second state and put it in the first state. So these are some unsolved models of molecular physics, which one can be interested in. And this u of x is the diabatic potential surface. S of x is the coupling, which says at what conditions the population should transfer from one to the other. And we will so how do we know what choice of potential energy surface and what choice of coupling should we use? So one can have a ab initio first principle calculations of what can be the potential surfaces. So there was some time before where there was a belief in the electron transfer community that the electron transfer happened in this way. So this blue colored curve is the initial state, and this orange curve is the final state. And then people thought that the electron transfer, when the electron has transferred, uh, the molecule just jump from this coordinate, being from this coordinate to exactly this coordinate. But there is a problem, and this was done by Libby, and he was successful in explaining all the observations of electron transfer processes during those times using the solvation barrier. So there is a barrier here. In an instant of time, the solvation quickly jumps from one coordinate to the other, and he was able to explain using this energy barrier. But there is a problem that at a given instant of time, if this energy has jumped from a value to another value, then the energy of the conservation of energy has been violated, which is a serious problem which he did not notice. And then this was severely criticized by Rudolf Marcus. He is a Nobel laureate. He got Nobel Prize for the work he has done on this electron transfer, in the understanding of electron transfer. He proposes that the reactants, the picture that I show is the wave function picture. So the reactant can be some maxima in some configurational space. The product can be some maxima in some configurational space, and then the activated complex that I showed is also some wave function overlap. And these all wave functions should be eigenfunction of the same Hamiltonian, and which means that the energy at all instants should be the same, meaning there should not be any jump in the energy. The energy should be conserved at all time. So this was his proposition in a simple words. Picture given by Libby is not correct, and the one needs to understand the electron transfer process in this manner, where if it is in a thermal equilibrium, if the electron transfer is in a equilibrium, then at the end it will be in equilibrium, and when the reaction happens, the energy at the point should meet. So when they encounter, the energy should match. So so he- so now it is his duty to derive what should be the coordinate, what should be the relevant coordinate that is changing in the electron transfer process, and what kind of diabatic surface it should be. It should be so far I have been showing you a parabolic kind of energy, but then he wants to derive from principles because he is doing the work for the first time. So he asserts that the solvation energy difference. So this mathematically means the solvation energy difference, where the D's are the electric displacement vectors due to the reactant and product ions. They are charged particles, and P of R is the polarization function that reflects in the solvents. So an alternative simple definition is the difference in the kinetic energy between the difference in the difference in the electrostatic potential energy between the donor and the acceptor. So having suggested what should be the coordinate, he proceeds on to the form of the potential surface. So he writes an equation for a Green's function starting from electrodynamic equation, and then the nature always chooses a surface which minimizes the free energy. So he writes a Lagrangian functional which can minimize this free energy, and he constrains that the total energy is conserved. So this means that the total energy is conserved, which is absent in the Libby's theory. So he introduces this, and he obtains that the free energy surface should be exactly parabolic, and lambda x is the solvent reorganization energy. So in the animation that I showed, you see that the molecules arrange themselves in presence of solvents, and there is an energy that is needed to arrange themselves. That is exactly called the solvent reorganization energy. So for the product states, so here he did it for the reactant state, and again he does it for the product state, and he again minimizes his free energy functional, and he finds that the product is displaced twice the solvent reorganization energy. The spring constant is also given by free energy solvent energy, and there can be additional free energy change during a reaction which determines the spontaneity. So here one can see that the reactant is centered around 0, and the product is centered around 2 times solvent reorganization energy. So in the animation that we showed, we saw that the solvent has to reorganize twice before doing an electron transfer. So this general feature has been captured by, and depending on the solvent reorganization energy and the free energy, one can categorize the chemical reaction. The solvent reorganization energy is useful in promoting an electron transfer reaction, whereas the free energy change is the energy required to complete the reaction. So if the reorganization energy is exactly equal to the energy required, then you can see a barrierless reaction that I show here. Then the population need not climb any potential surface. They can just immediately relax to the product state. On the other hand, if the available energy is less than what the energy required for the reaction, then one has to climb this barrier. This barrier has to be overcome by either external fluctuations or internal solvent fluctuations, but there is a barrier. But what was not known during his time is that even if the available energy is more than the energy required, there is still a barrier, because And for quantifying all of this, he got the Nobel Prize. But let us not get into his work. We will get into the work that I did in my PhD. So such models can capture any reversible reaction, not only the electron transfer process, any chemical reaction or any dye molecules which relax to ground state to excited state and things like that. So here you can see that there is a reactant energy surface and product energy surface. They are coupled at a single point. This is because the energy conservation should be valid. So they should be having a form of a Dirac delta or a Gaussian. Yes. So such reactions can be important in understanding various complex reactions. We have simple models, and for example, there are catabolism and anabolism, where the food molecules are being broken down to energy ATPs, and or the available extra energy is built back into proteins or muscles that we gain. So the catabolism anabolism is a reversible reaction process. It consists of lots of electron transfer and reversible reactions. And this is one part of digestion, glycolysis, where there are 7 reversible reactions and 3 irreversible reactions. So it becomes important to quantify such chemical reactions on a molecular level to understand them. So in the context of material science, the material scientists would be interested in understanding the charge transfer spectra, which is just coming from the UV visible absorption photospectrometer. And such absorbance spectra can be exactly quantified if one solves a model like that. There is a ground state, one shines a light, and it goes to a locally excited state, and there can be charge transfer bands which can influence the ground state relaxation. So one can these are the list of examples is slightly bigger. So this can be all vision. So during eye vision, what happens is that inside eye we have a retinal protein, and so if a light falls on it, it changes its form from trans to cis, and then it releases an electrical signal which we interpret it as vision. So in the molecular understanding of vision, it's an isomerization process. It's a reversible process. So one can use it. One can use such models that I showed, the diabetic representation, to exactly quantify the eye vision process. So here I will consider a very simple model. So I showed you harmonic oscillator. Here in my PhD, we reduced it to a simple model of potential which are flat. They are not like parabolas. They are instead flat like this. And you can see that the population can go from one state and enter into the other state similarly, and vice versa. The population which is exactly getting reduced from one state goes to the other state. And the initial population can be Gaussian in one state, and it can be Gaussian or zero in other state. The difference in these initial conditions I will emphasize in the upcoming slides. So how do we solve is not of much interest, but if you have a partial differential equation like this, one can write it in its operator form. You can do Fourier inversion, and then you will have and then if you reduce it, you will get some kernel which is not exactly Fourier kernel, but this kernel allows us to introduce all the potential, all the boundary conditions. So this was the method devised by us, which is not exactly the Fourier method. uh, and uh, and we show how successful it works. So this is the excited state and ground state distribution. So I can be reactant or product, and I can calculate the population in both of them. So I can integrate the probability distribution and get the population in both the states. I will use these profiles to further discuss the physics. So how do we know the solution is correct? This is for the students, that you have all the boundary conditions, you have all the conditions for a good mathematical solution. You have to check on them. I checked on the boundary condition, substitute back into the original equation and check whether it's correct or not, and then got some solutions using computer, and then compared them with the exact results that I got. So using this, we can understand what is called Lee-Chatterley's principle. So assume that if there is a reversible reaction, and if the conditions favoring the forward reaction and the backward reactions are the same, then there is no interconversion. Maybe the reactants and products are converting between each other, but the conversion is very equal and there is no net change. So this can be understood as a multidimensional seesaw. If the parameters, there are several parameters that influence the direction of a reaction, and if they are all on the midpoint, then there is no change. This situation is called dynamic equilibrium. And if one parameter that favors product is increasing, then you can see that the product weighs more, and if the parameter that favors reactant is increasing, then the reactant is more. So this is called this is the Lee-Chatterley's principle in a simplified form. And in the literature, it is known that one cannot prove the Lee-Chatterley's principle. It is just a generalization based on the experimental evidences, and then we solved the problem for the first time. So this is the population that I got using mathematical model. So if the reaction, if the rate of forward reaction and rate of backward reaction is same, then there is no change in the population product. If the rate of forward reaction is more, then obviously I am going to harvest more products. But if the rate of forward reaction is less, then I'm going to harvest more and more reactants. So if one takes the ratio of the population of products and the reactants, I can see that it is exactly the ratio of the rate of reactants, which is called the equilibrium constant that one studies in the physical chemistry context. So this is our first success, where we were able to show we start from a non-equilibrium description molecular model, we solve the exact dynamics, and then we arrive at a macroscopic law which is already known in the community, which has no theoretical proof. And then but the Lee-Chatterleys have given his conditions for breaking the dynamic equilibrium with the temperature, pressure, volume effect he has captured. But we capture in more detail, because we are handling non-equilibrium system. His laws are valid at equilibrium, so our laws are even true in the non-equilibrium setup. So we are able to probe more effects than what he has been able to capture. So here I have chosen the forward rate to be greater than the backward rate, so one can see that you will receive more products. But the temperature in the reactant molecule configuration is more than the temperature in the product state, meaning if the temperature is more in the reactant state, so once the reactant has formed, they immediately move away from the reactant configuration. For example, if a molecule rotates and then it forms another molecule, and then if it immediately moves away from that configuration, they will not come back again to the system will not be reversible. So similarly, if I increase they will immediately move away from the reactants, and the system will behave like an irreversible process where the interconversion is stopped. So similarly, if I I can place my reactant molecules near the near reactive configuration. I'm unable to see. So I can place far away from the reactive configuration the reactants, or I can place the products far away from the reactive configuration, and the chemical kinetics changes its direction. So one can exactly quantify all these non-equilibrium laws. So at equilibrium, you can see that laws are different, and at during non-equilibrium times, the laws are different. Is what is the essence, general essence of what I'm stating. So I can also so all the molecules will not have same configuration. For example, if I have a collection of reactant molecules, then all their bond lengths are not going to be the same. All their bond angles are not going to be the same. So they will have a deviation in the from the mean configuration. So this is the effect of mean configuration. If the reactant has a high high deviation, then the chemical equilibrium is achieved very fast, and the total population is always one. So here I will so far we have considered a situation where in both the reactant state and product state the population are there. So what happens if I remove population from one of the states that I show here? So I have a ground state, I remove all the populations and leave only the Gaussian in the excited state, and we got a solution which matches with the results of computer, and they undergo all the checks correctly. So this is the situation in the Lee chat list. So if you have both the population same, then you have a condition dynamic equilibrium. If you take out some products, then what happens is that more products will start to form. So this is the Lee chat list effect of concentration, and it will start, reactant will start to deplete, and product will start to populate. Okay, so if I completely remove the products, then what will happen? So more products will form, and more reactants will deplete. So that is what exactly we see here. So even if I have forward rate and backward rate to be having the same numbers, so here I have chosen the forward transfer and backward transfer to be the same, but still I will receive more number of reactants will deplete and products will form, which is exactly the Lee Chatley's principle on the effect of concentration. And one can one can play with the rates of forward and backward transfer. One can break the uh, symmetry, and then one can have more yield. So if I have more rate of forward transfer, then I can have more products, so which is deviating from the. So here we discuss the effect of temperature and viscosity. So the diffusivity is related to the temperature of the solvent and viscosity of the solvent, and one can see the effect in the product conversion. So one can also apply these reactions into electronic relaxation, where one can have more insights into what is happening when we really take an observance spectra. So imagine that there are dye molecules, they are immersed in solution, and then the uh, light is shined at it, and in a molecular in the bone opener picture, one can see that it looks like this. And once the light has shined, the population goes to the excited state. This E is the excited state. And if the wavelength is very small, meaning the energy is very high, one can excite to the point here. If the wavelength is very very high, meaning the energy difference is small, one can excite it to here. So from the position of the wave packet that you have just excited, one can understand the effect of excitation energy or the excitation wavelength. And one can always so when one excites, the population does not always excite to a particular configuration. It can it can excite to nearby configurations, meaning that they deviate from the mean configuration, so which is giving the effect of the bandwidth of the light. So so this is the effect of excitation wavelength on the transient decay. So if one measures time dependent population in the excited state, one can show that the excitation wavelength has such dependence. Yes, someone has a question. Okay. uh, so if the excitation energy is very small, then one can see that one can have a very fast excited state decay. And this is the effect of bandwidth. If the light has if the light is very polychromatic, it's not of a single wavelength character, then you can see that the chemical equilibrium, or the equilibrium between the excited state population and ground state population achieves very faster. So sigma is, when the bandwidth is very more, then the equilibrium is very faster. But in the literature, this two state model has been solved for the first time. So people have solved only for one state, either the excited state or the ground state. So here is the mathematical derivation of their results in the light of our results. So I can derive asymptotic results using mathematics for such conditions where the rate of backward transfer is much greater than the forward transfer. So you imagine if a reactant is forming a product and the back conversion is very faster, then the reaction would never happen. So it would, if it starts from a population 100 percentage, it will remain to be 100 percentage. This is the normalized population. And let us say if the forward rate is much greater than the backward transfer, then you can assume that there is no back transfer, and then you can it consider only one state, just like in the literature has been considered. What if they both are very high? Then, as usual, we know that only the ratio does matters, because I showed in the graph of equilibrium constant, if the ratio is same, as far as the ratio is same, the population profile is going to be the same. So one can use such a simple formula to capture even for smaller rate of transfers. So this is the graphical result of the result that I just explained. If the backward transfer is very high, then there is no reaction at all. If the forward transfer is very high, then there is no backward transfer. The reaction proceeds like a irreversible process. And if they both are high, then the ratio decides which way the reaction would move. So these are the conclusion of this work, that in the literature we have solved the two state model for the first time, and people have given in the Laplace domain, where one has to assume first order chemical reaction even in fitting the transient, even in fitting the absorbance spectra. People assume first order or sum of first orders. But in our profile, we don't need to assume any first order. We have presented profiles that is useful for the experimentalists to fit their transient absorption data, and the profile has all the details of the molecular parameters. So one can appoint these profiles to, one can employ these profiles to understand the molecular parameters behind their dye molecules that they, and we have explained the concepts such as dynamic equilibrium constant, Le-Chatelier's principle from theoretical model, which has been experimentally observed. Now I am going to move on another problem, which can be interesting to of undergraduate students. So we study where a wave packet, it comes, it interacts with the potential barrier, and then let us see what happens. So such type of systems can be useful in understanding. So let us say this is an wave packet of an electron, and then it encounters a barrier in a nano device, or it is true even for molecular process, where you have a wave packet, and it interacts with the reaction barrier, and then let us see, I mean, in what rate the reaction would happen, and in what way, through quantum mechanics. So this is the model for isolated molecule. So one can solve this model using the mathematical method that we developed, and this is the result. So one can see that at t equal to 5, the distribution approaches the barrier, which is at the center, and at t equal to 10, it even disperses, and then at t equal to 25, it exactly encounters the barrier, and then you can see that there are multiple reflections in the left hand side, and there are some leaking into the right hand side, over barrier and the tunneling. This has the contributions from over barrier and the tunneling both. And after a while, you will see transmitted wave packet that moves right, and a reflected wave packet that moves left to the barrier. So here I have shown the difference between the Dirac delta potential and the thin rectangular potential that I showed. So here this is a very thin rectangular potential, and this problem has been solved for the first time. So these are the dwell probabilities, meaning these are the probability to stay in the left hand side of the barrier, and this is the probability to stay in the right hand side of the barrier, and these dotted curves are the probabilities to stay inside the thin rectangular barrier. So one can see that when the wave packet approaches the barrier, the probability to be inside the barrier increases, and then again it decreases because the wave packet starts to leave the barrier, and some of them goes right and some of them goes to the left. Probability is not normalized here. And here we show the effect of barrier height. If one increases the effect of barrier height, the localization on the left hand side increases. So here it goes in 10 orders of magnitude, and the distribution increases correspondingly. So now I calculate the statistical properties of the wave packet. The mean of the wave packet behaves like a refraction inside the lens. So if the potential effect is very meager, then the wave packet that starts from -8 starts to move and then doesn't get deflected. If the potential is very high and the width is also very high, then they start to deflect, which is like the refraction of light in a lens. And one can also apply such models to study properties, the refraction properties of light. Now I have calculated the width. So the width stays the same and then starts to increase because there is a diffusion when the wave packet evolves. There is a diffusive effect, and then once they interact the barrier, the width heavily decreases, meaning the wave packet is shrinking. So this is exactly the effect when you do a measurement. So what happens that we have studied that when you do a measurement, the wavelength the wave function localizes to a point and then we get a result. So this thin rectangular barrier is a potential, is like a measurement, it's a weak measurement. So you can see that the wave function collapses. It localizes into this space, and after that it again delocalizes. So one can also start from an exponential function. So the initial function can be Gaussian or an exponential, and one can solve that also. So now I would like to conclude my talk. So these are the other solvable models. I have showed only 2 works that I did in my PhD. There are other solvable models where you can solve such molecular models. So in the diabetic picture, you can reduce it to single state, and then you can solve under various limits. Reaction like this, there is a W like barrier, there is a reactant, there is a product, there is an activated complex. So one can study how reactants cross over this barrier. This also we solved for the first time. And in quantum mechanics, we solved these all problems where one can capture the vibrational transitions between a diatom, and electronic transitions between the excited state and the ground state. You have transitions, and then you can capture the general loss. And then here the transition can happen from anywhere from the surface, but here the transition can happen only at a single given point. So such models can be useful in various problems. So the problems that are still open is if the potential is harmonic, and if the sink is a Dirac delta is still problem, because I showed only results of flat potentials where the potentials are like this, not like this. And one needs to solve double wall problem. This is an open problem which is known in the physics community. It has not been solved in the quantum mechanical and classical mechanical both limits. So the future hope is to solve more realistic models so that it can be useful for experimentalists and molecular physicists to develop a software so that you can solve any potential models and any sync functions. And then inside the solvents, the potentials are not static, they always dance. So to solve moving potentials and moving boundaries and incorporating more and more, so far I solved only one dimensional models. Your molecule can have multiple dimensions, and then you need to obviously extend your approach to multiple degrees of freedom. And then you can use quantum dissipative models in the when as far as dissipative was concerned, I showed only classical mechanical evolution. So if one uses quantum mechanical evolution, one can see how each vibrational state contributes to a solvation and the electron transfer process. And then one needs to derive more new governing equations like Smolachowski equations for different noises. So far we assumed only what is called Markovian noise, which is memoryless noise, using path integrals. And then there are more applications to this work, like self-organization, the pattern formation on leaves can also be understood using reaction diffusion systems. Stochastic resonances are all the one can move in an advanced level by applying all these theories. And in quantum mechanics, again, to solve more realistic two-state models, to develop efficient algorithms to solve arbitrary potentials, which is also useful in the nanomaterials community. And the methods of chapter 2 can be extended and to solve models that show Bose-Einstein condensation, that capture the general features of Bose-Einstein condensation. And then one can have dependent potential energy surfaces to study the Artostechnian physics of high harmonic generation, such big complicated behaviors. I would like to thank my PhD supervisor, Dr. Aniruddha Chakrabarti at IIT Mandi, and Professor Raphael David Levine at Hebrew University of Jerusalem. He has won a prize which is next to Nobel Prize. It's Wolf. He has won what's called Wolf Prize. So I would like to thank you all for coming. If you want to read more on this topic, then I have a book with my supervisor, and there is a book which is already available. One can note down. So thanks.
Excellent presentation, sir. Thank you so much for giving a nice lecture, sir.
Thanks.
Dear participants, if you have any question, you can ask our sir.
You are free to ask any questions, and you are free to interrupt, but
Dear
students.
participants, if you have any question, you can ask.
Okay.
சார் நாங்கெல்லாம் எக்ஸ்பெரிமெண்டலிஸ்ட் தியரிட்டிஷனை பார்த்தாலே பயப்படுவோம்.
பரவாயில்லண்ணா. அது டாக் பிளான் பண்ணும் போதே தெரிஞ்சு கொஞ்சம் டஃபா தான் இருக்குன்னு. இன்னொரு டாக் இருந்துச்சு, அது வந்து வெறும் நானோ மெட்டீரியல்ஸ்க்கு அப்ளிகேஷனா. அது எப்படின்னா, இது டிரான்ஸ்மிஷன் ப்ராப்பர்ட்டிஸ், அப்புறம் ரெசனன்ட் டிரான்ஸ்மிஷன் இதெல்லாம் கால்குலேட் பண்ற மாதிரி. அது நான் எப்பயாவது
சார், I have one doubt, sir. Sir?
Yes, please.
Sir, how to start up in nanomaterial research and material science, sir?
மெட்டீரியல் சயின்ஸ் ரிசர்ச்சுக்கு இப்போ உங்களுக்கு இப்போ நம்ம ஊர் ஃபுல்லா நிறைய ஆப்பர்ச்சுனிட்டிஸ் இருக்கு. உங்களுக்கு ஃபாரின் வரணும்னா சொல்லுங்க. இங்க இஸ்ரேல்ல நமக்கு ஃப்ரெண்ட்ஸ் எல்லாம் நிறைய லேப்ல இருக்காங்க.
இல்ல சார், இப்போ
நம்பர்
இப்போ
ஸோ
இஸ்ரேலுக்கு
நீங்க அப்ளை
நாங்க
பண்ணீங்கன்னா அவங்க எடுப்பாங்க.
ஓகே சார், ஓகே சார். சார்
நீங்க
இப்போ
வந்து சொல்லுங்க.
இப்போ ஐஐடி ஜாம் ப்ரிப்பேர் பண்ணிக்கிறோம் சார்.
சரிப்பா.
இப்போ அதுக்கு வந்து இப்போ ஜாம் வந்து இன்டகிரல் பிஹெச்க்கு வந்து ஜாம் கிளியர் பண்ணுமா சார்?
ஆமாப்பா, ஜாம் கிளியர் பண்ணணும்.
இப்போ நம்ம ஐஐடி என்ஐடில கிடைக்குமா சார் அந்த இன்டகிரல் பிஹெச்டி ஜாம் கிளியர் பண்ணனா?
ஜாம் எழுதுனா ஐஐடிஸ் என்ஐடிஸ்
ஓகே சார். ஓகே சார், தேங்க்யூ சார்.
யார் பேசுனது? வைத்தீஸ்வரியா? யாரு பேசுறது?
இல்ல சார், ஹரீஷ் சார். ஹரீஷ் சார், ராஜா சார்
நீங்க
ஸ்டூடெண்ட்
வந்து
சார்.
ராஜா சார் நம்பர் எடுத்துக்கோங்கப்பா. உங்களுக்கு எதுனாலும் வேணும்னாலும் நீங்க எதுனாலும்
ஓகே சார்.
வேணும்னாலும் நீங்க கேட்கலாம். உங்களுக்கு என்ன மாதிரி
சார், ஐ ஹேவ் நம்பர் சார். யுவர் நம்பர் சார், ஐ ஹேவ்.
சரிப்பா.
ஓகே சார்.
சண்டை போட்டுருக்கோம் சார். இல்ல சார் வந்துட்டு அது அப்படியே சொல்லாம பரவாயில்ல நம்ம ஸ்டாஃப் எல்லாம் அப்படி இல்லைன்னு ஒரு மேனஸ்ல போட்டிருக்காரு. அதனால யாரும் சண்டை போடல. பார்த்தேன். அப்படியா சார்?
Hello, dear participants, please mute your audio and video mode, please. If you have any question, you can ask. Thank you so much, sir. Professor Dhananjayan, are you there? Professor Dhananjayan? Okay. Now he's going to give a vote of thanks. Thank you, sir.
Very good afternoon to all. It's my pleasure to deliver the vote of thanks on behalf of our department. I would like to thank our chief guest, Dr. R. Saravanan. We are really enlightened with your knowledge and presence, and your session is very helpful one for the young researchers. Thank you, sir. Next, I would like to thank our management and principal, head of the department, for their support and make this program a great success. Then I would like to thank all the participants from various colleges and universities who are present here. Finally, I thank all the staff members for your cooperation in making this occasion a great success. Thank you, sir.
Thank you so much, Dhananjayan sir, and faculty members, students from other institutes. Tomorrow, sharply, we will have another session. Exactly 5 to 7. Okay. Thank you so much. Thank you, Dr. Saravanan sir. Thank you, sir.
தேங்க்ஸ் அண்ணா. தேங்க்ஸ் ஆல். நீங்க
Thank
எதுனாலும் டவுட்ஸ் இருந்து பொதுவுல கேட்க கூச்சமா இருந்தா கூட நீங்க வாட்ஸ்அப்ல கேட்கலாம். ஸ்டூடெண்ட்ஸ் ஆர் மோர் வெல்கம் டு இன்டராக்ட்.
Thank you so much, sir. Thambi, feedback link. Dear participants, please kindly fill the feedback form. Thank you.